In this video, we're going to talk about using Boltzmann factors in the partition function in order to find out about the average value of the energy of some system. So to review, our Boltzmann factor is given by e to the e, so e raised to the energy divided by kT, negative. This factor here, if you remember from the last video, is proportional to the probability of finding a particle in some state if it is in equilibrium, in thermal equilibrium with some reservoir at temperature T. Now we're going to use a slightly different notation here. We're going to replace kT with beta, which is just going to turn out to be handy later on. So we will write this as e to the minus beta times e. We have our partition function. The partition function is simply the sum of all of the Boltzmann factors for a given system, which is going to be the sum over I of e raised to the negative beta ei. So we're going to sum from I equals 1 to n, where n is the number of states that are available to our system. Okay, and now the probability of finding an atom in a particular state I, which has some energy E sub I, is simply the Boltzmann factor for that state divided by the partition function. Okay, now what we want to do in this video is actually talk about how we could predict the average energy of a particle in some system at some given temperature. So what we're really going to do is we're simply going to take a weighted average of the energies where each energy level is weighted by the probability of finding the particle in that state. So the equation that we're going to use is that the average energy is equal to the sum over all of the states of the energy of that state multiplied by the probability of finding that state. Writing this out explicitly, we have E1 times P, the probability of state 1, plus E2 times the probability of state 2 plus dot dot dot. So what we're doing is we're basically weighting each of the energies by the probability of a particle being at that energy. Now let's look at a specific example of calculating the average energy of particles in some system. So imagine that we have atoms which have 3 available energy states. They can be in the lowest energy state, E1 or E2, which have these values. And let's imagine that these atoms are in equilibrium at a temperature of 1000 Kelvin. Okay. So the first thing that we're going to do is we're going to calculate the Boltzmann factor for each of these energy states using the given temperature. And we're going to use the Boltzmann factor in electron volts, since that is the easiest to use here. The Boltzmann factor for each of these states is given here. And we've also calculated the partition function by simply adding up all of the Boltzmann factors, and we get 1.108. Okay. Now that we have our Boltzmann factors and our partition function, we can calculate the average energy. So the average energy, we simply take the energy of the state and we multiply it by the probability of that state. It's Boltzmann factor divided by the partition function. And we do this for each of the states and add them up. In doing so, we end up finding 0.021 electron volts as the average energy of a particle in this state. Of course, no particle actually has exactly this energy. Each particle has one of these discrete energy values, but when we average over many particles, this is what we would expect to find for the average energy. Note that the Boltzmann factor for the ground state is 1, and for the first excited state is only 0.098. So the vast majority, 90-ish% of our particles are in the ground state, with only about 10% in either of the 2 excited states, and only about 1% in the second excited state. Okay, which leads us to believe that our average energy should be close to the energy for the ground state, which is 0 electron volts in this system. So this is an expected number in that it is closest to the energy of the state, which is by far the most probable state. Now let's look at this same system, except now we'll introduce degeneracies into the energy levels. So let's imagine that we have one ground state, but the first excited state really has 4 different states, all with the same energy of 0.2 electron volts. And likewise, the second excited state, there are actually 16 different states, each with 0.4 electron volts as their energy. This is going to make it more likely that the particles will be in some excited state because there are simply more excited states for them to be in. Okay, our Boltzmann factors have not changed because our energy levels haven't changed. The partition function will change, however, because we need to take into account the degeneracy of the energy levels. So remember that the partition function is the sum of the Boltzmann factor for every single energy level. Right? And there are now 4 energy levels with an energy of E1. So I need 4 Boltzmann factors. I need to add up that Boltzmann factor 4 times, which is equivalent to just taking that Boltzmann factor, the say E1 Boltzmann factor, and multiplying it by 4. That's the same thing as adding it 4 times into my partition function. The same thing for the E2 state. That is going to have a degeneracy of 16. So we're going to add 16 Boltzmann factors into our partition function, which is the same as adding the Boltzmann factor for the energy level 2 multiplied by 16 into our partition function. When we add all of these together, we get a Boltzmann factor of 1.552. Okay, now that we have our Boltzmann factor and our partition function, we are ready to find the average energy. So what we are going to do is we are going to take our energy levels and we're going to multiply the energy level by the probability of finding that energy level. And now, again, we have to take into account the degeneracy because there are 4 energy levels with E1, right? And there are 16 energy levels with energy E2. So we need to multiply by that factor in order to take into account the 4 energy levels with the same energy of 0.2 electron volts. Okay, putting this into our equation here, we end up with an average energy of 0.092. Now this is higher than we found before. It's still very close to our 0 energy, but it is getting much closer. It's about halfway between these 2 energy states. By adding in these degenerate states, we now have a larger probability of the electron being, or the atom being in an excited state, because there are more excited states available, and therefore the average energy of the particles has increased. Now let's take a moment to look at a quick math trick that will actually make some of our future calculations easier. So what we're going to do is we're going to look at the partial derivative of the partition function with respect to beta. If you remember, beta is 1 divided by kt, but it turns out that it's actually handier to write it in terms of beta because of this trick. Okay, so if I take the partial derivative of z with respect to beta, well, that looks like the sum over all of the states of the partial derivative of the Boltzmann factors with respect to beta. We'll pull down a negative ei when we take this derivative. And so what we find is that this partial derivative actually equals negative the energy multiplied by the Boltzmann factor divided by the partition function for each state, which looks exactly like our weighted average. The energy multiplied by the probability for each state summed up, which is our definition of the average energy, and we have a minus sign up front because of the minus sign pulled down when we took the derivative. So in general, what we find is that the average energy can be found by the negative of the partition function, or 1 over the partition function, multiplied by the partial derivative of the partition function with respect to beta. Now let's take a moment to look at a quick math trick that will actually make some of our future calculations easier. So what we're going to do is we're going to look at the partial derivative of the partition function with respect to beta. If you remember, beta is 1 divided by kt, but it turns out that it's actually handier to write it in terms of beta because of this trick. Okay, so if I take the partial derivative of z with respect to beta, Well, that looks like the sum overall of the states of the partial derivative of the Boltzmann factors with respect to beta. We'll pull down a negative EI when we take this derivative. And so what we find is that this partial derivative actually equals negative the energy multiplied by the Boltzmann factor divided by the partition function for each state, which looks exactly like our weighted average. The energy multiplied by the probability for each state summed up, which is our definition of the average energy, and we have a minus sign up front because of the minus sign pulled down when we took the derivative. So, in general, what we find is that the average energy can be found by the negative of the partition function, or 1 over the partition function, multiplied by the partial derivative of the partition function with respect to beta. Now let's consider the system of a two-state paramagnet. So a two-state paramagnet has electrons, or some atom with spin, but we'll just call them all electrons here. So imagine that we have some electrons which can align or anti-align with an external magnetic field. So these blue arrows represent the direction of the magnetic moment of the electrons. So in general, the electrons will attempt to align their magnetic field with the magnetic field of the generated externally here, right? Just like a bar magnet will tend to align with another bar magnet so that their two fields point in the same direction, the electrons will tend to align with the direction of the external magnetic field. Now, due to quantum mechanics, the electrons actually only have two options for states to be in. They can either align or they can anti-align. And it's also possible that they will anti-align with this magnetic field. And the electrons aligned with the magnetic field will be in a lower energy state than the electrons that are anti-aligned, because there's going to be a force on these electrons attempting to flip them into the aligned state. The stronger the magnetic field, the stronger the force attempting to flip them into the energy or the up state here, the aligned with the magnetic field state. To find the energy of each of these states, we can use the equation energy equals negative mu dot B. Mu tells us about the strength and direction of the magnetic field for the electron, and B is the magnetic field, the external magnetic field. When the electron's field or magnetic moment points in the same direction as the external field, we end up with negative mu times B as our energy. And when they are anti-aligned, we end up with positive mu times B, because we pick up an extra minus sign from the dot product, from the magnetic moment being anti-aligned with the external magnetic field. Okay, so we have two energy levels with different energies. We have the low energy state where the spin of the electron or the magnetic moment of the electron is pointing up, and we have the high energy state where the magnetic moment is pointing down. Now we can calculate the partition function for this system. And again, we're just going to add up the Boltzmann factors for the two states. In the case of the electron pointing up, we have e to the plus beta mu times magnetic field. Remember, beta is 1 over kT. And we can do the same thing for the down state. Now, it's actually going to be slightly more convenient mathematically to, instead of writing this in terms of e's, write it in terms of hyperbolic trigonometric functions. Specifically, we can use the relationship that the cosh of some variable is equal to e to the variable plus e to the minus that variable, so here theta, all divided by 2. So this here looks like the cosh of beta mu times b, and we have a 2 out front because there's a 2 in the denominator of this equation. And real arguments here simply means that theta must be a real number. Theta is not an imaginary number. Okay, now we can use the trick that we just learned to find the average energy of this system. So what we're going to do is we are going to take the partial derivative of the partition function with respect to beta. The derivative of cosh is sinh. So we have a sinh of beta mu times b, And then we have a mu times b from the chain rule here when we take the derivative of the inside. There is also a minus sign out front here, but that comes from our general equation. That didn't come from the derivative. Okay, and then we divide it by the partition function, which is our cosh. Just like for sines and cosines, sinh over cosh equals tanh, or the hyperbolic tangent function. So our average energy equals this equation here. Now let's look at the graph of this tanh function and see what it means about the average energy that we expect these particles to have, depending on the strength of the magnetic field, the temperature, and their magnetic moment. Okay, so first, let's look at magnetic field strength, or mu. If mu gets stronger, that means that the particles are more magnetized and they should feel a stronger force due to the magnetic field. If the magnetic field is stronger, the particles should also feel a stronger force due to the magnetic field. In both cases, if mu or b increase, we would expect that more particles would align with the magnetic field, which means that we would have more particles in the up state. And since the up state has an energy of negative mu times b, we would expect our average energy to get very close to all of the particles are in the up low energy state. And we see that our tanh function actually approaches negative mu times b as we get to strong magnetic fields or high magnetic moments. On the other side, we can think about K times T. Well, if I move to a very high temperature state, then my denominator gets very big and this whole thing moves closer and closer to zero. So let's see what happens to tanh as I move closer and closer to zero. Well, in that case, I'm going to get a expected energy, an average energy, that is going to be close to zero here, which means that the particles are going to be effectively randomly arranged. That is, that the particles will not necessarily be highly correlated with the magnetic field, but they will be randomly arranged. Now, if we think about this in terms of multiplicity, the maximum multiplicity state should occur when we have completely arbitrary states in terms of up and down, that we don't prefer the particles to be up, we allow them to randomly arrange themselves, right? So say half up and half down is going to give us the maximum multiplicity state, and we would expect that we are going to reach the maximum multiplicity state when we are at the highest possible temperature. So as our temperature gets very, very high, our particles move to basically 50-50 up and down, which means that our total energy, which is just the sum of our up energy and our down energy, is going to get to zero, because we're going to have half of the particles with a positive energy, half of the particles with a negative energy. The total energy of those added together will be zero. So as our denominator gets very large, our average energy actually, it increases, but it increases towards what we have called zero. So we can see that this tanh function actually makes a lot of sense in terms of our expected average energy based on temperature and field strength. As field strength increases, we get more particles aligned up with the magnetic field, which are in low energy states, and our average energy per particle decreases. As temperature increases, our function moves towards a very low value. We're taking the hyperbolic tangent of a very low value here, which is going to bring us to a expected energy level of zero, because we'll have an even number of up particles and down particles.